This video describes the paper entitled Order-Disorder Transitions in a Minimal Model of Active Elasticity by Guozheng Lin, Zhangang, and Cristián Huepe. Introduction and motivation. We can classify the models of active agents that self-organize into collective motion into two classes: velocity-based, where the velocities or heading directions are matched between neighbors, and position-based, where only information on the relative positions is exchanged, not the velocities or headings. We introduce here the active elastic alignment model, which combines both while describing a mechanical system with elastic interactions. It has a mechanical interpretation, rich critical behavior, and multiple potential applications. Model description. We imagine two self-propelled carts, these gray discs, with wheels, the orange lines, and a frontal projecting arm, the blue lines. Due to the wheels, these carts cannot move sideways, only forward, backwards, or turn. Since the elastic forces are applied at the tip of the arms, they introduce torques that rotate the heading directions and forces that add or subtract from the self-propulsion. R controls how much the forces depend mainly on relative positions for small r or on relative headings for larger R. These are the resulting equations for the positions, heading angle, and linear elastic forces. Self-organizing dynamics. This simulation shows the self-organization of a system of 100 agents attached by springs in a periodic lattice. Transition to dynamic disorder. This bifurcation diagram presents the polarization as a function of noise for different R values. We see that the transition goes from discontinuous on the left to continuous on the right as R is increased. This is consistent with previous results showing that position-based algorithms have a discontinuous transition, while velocity-based ones have a continuous transition in small systems. Transition to quench disorder. This bifurcation diagram shows that we find a different transition for a larger value of R, presented here in blue. This new transition exhibits a steep drop in the level of order and a sharp rise in the fraction of springs that are resisting opposing self-propulsion forces. It is a transition to a state of quenched or frozen disorder, as we can see in this simulation, where the red crosses show the points of opposing self-propulsion forces. These divide the space into fixed regions that are locally ordered but globally disordered. Large system analysis. Up to now, we have focused on simulations of the AEA model in relatively small systems of 100 agents, which is an interesting finite-sized case with real-life applications. Here, we will analyze what happens in large systems of up to 40,000 agents. The diagram shows that the three types of transitions are still present, but the velocity-based order state that produces the continuous transition starts to decay in larger systems. This is consistent with the Mermin-Wagner theorem, as explained in the paper. In the thermodynamic limit, we expect only the discontinuous order-disorder transition to remain, and that dynamic disorder will transition to quench disorder at higher noise and for large enough R. We note that the newly identified state of quench disorder is still observed, and that its frozen nature is more visible in the large simulations, as shown here.